In the last 2 decades, the IP protocol has become the most prominent, important layer 3 protocol in the world. And in this talk, we're going to discuss some of its features. So the IP protocol is a ubiquitous layer 3 protocol. It is deployed over any layer 2 protocol available, and basically you can find IP protocol devices anywhere on Earth. It presents a layer 4 a service of an unreliable, connectionless packet delivery between end hosts. That is, it does not guarantee the delivery of the packets. It does not require a connection establishment, but it will do its best effort to actually deliver the packets. The other thing that IP gives us is a global addressing scheme, which we can use to uniquely identify hosts worldwide. It is important to understand that IP doesn't give us everything. Since it is only best service, packets may be lost, may be duplicated, or may be delayed for unbounded amount of time. Packets may also arrive out of order due to these unbounded delays. In addition, there are no performance guarantee. We don't know if IP will give us any guarantee on the bandwidth, on the delay, or the loss. The main points we're going to discuss in this presentation are the addressing of IP, forwarding, fragmentation and reassembly, and error reporting and control messages. So in IP, each network interface has at least one IP address, which is unique. So machines with multiple interfaces have multiple IP addresses. For example, most laptops today have both Ethernet wired interface and a Wi-Fi interface. So they need to have 2 IP addresses if they are both active. However, there are some exceptions. Some IP addresses are not unique. For example, multicast IP addresses or anycast. Multicast is the case where I want to transmit a packet to a group of receivers. Anycast is the case when I want to transmit a packet to any one of a group of receivers, but not all of them necessarily. In IP version 4, which is the version this talk is going to concentrate on, there are 32-bit IP address. The address is hierarchical, divided into 2 fields, a network address and a host address. 3 classes were originally defined. There are 2 additional classes for multicast and one which is reserved for future use. So the class A address starts with a 0, has a 7-bit network address, and a 24-bit of host address. This enables us to build huge networks with up to 4 million hosts. Class B addresses start with 10, has 14-bit of network address, and 16-bit of host address. This can give us roughly 65,000 hosts in a network. And class C address has 2 to the power of 8. This is 256 hosts in a network. But it enables us to define many, many networks. The strict division of networks into 3 classes wastes address space. Suppose, for example, that I need 500 addresses for my network. I have 2 options. One to take 2 class C addresses, and one to take 1 class B address. In the second case, I'm wasting a lot of address space that I'm not going to use. In the first case, I burden the routing protocol because now I occupy 2 entries in routing tables. The solution came with something called CIDR, which dynamically partitions the IP address to network and host address. For example, the address 132.66.00/16 means that there are 16 bits for the network part of the address. And this is a typical type B network. This one belongs to Tel Aviv University. So you can see that it starts with 132. The next octet or byte is 66, and then I have 2 bytes for host address in this network. And binary, it looks like this, and indeed the first 2 bits in the network address are 10, as we expect for type B addresses. However, I can also define a larger network, for example, 132.64/13, which means that only the first 13 bits are the network address, and then I have 19 bits for host address. And this is Autonomous System 378, which contains Tel Aviv University. So as you can see, it enables me to define a hierarchy of networks, and this will improve routing efficiency because it can save entries in the routing tables. Some portion of the address space was allocated to private IP addresses. There are three address prefixes, which we call, that you see here, that were allocated for this case. And this is used in cases where organizations don't need to route outside of their network, but they still want to use the IP protocol. The good thing about it is that this address space can be reused by many organizations since it does not need to be globally addressed. So many places, like many of our homes, have this 10.0.0/8 address space, and we don't need to coordinate the usage of this address space because it is only local to our home or our organization. If we do want to go outside to connect to a global IP address from a private IP address space, there are two options. One is to use NAT, Network Address Translation. This is a device that translates my local IP address to some global IP address that is usually common to all the hosts in my network. The other option is to use a proxy server. That is, I'm connecting to a proxy server that has also a private IP address, but it has another interface with a global IP address, and all communication is going through this proxy. The use of number for addressing is very efficient, but it is not easy to remember, and people find it unattractive to use. Instead, we're having something called domain names, which is ASCII strings separated by period that gives us addresses for hosts in the internet. The domain name is built in a hierarchical fashion where you start with a host string dot subdomain, maybe multiple subdomain, then a domain, and then a top-level domain. What you see here on the right is an example, is a small portion of the domain name address tree. At the top you have the root, and below it you have what we call top-level domains. This can be either generic domain like .com, .net, or .org, or it can be a country code like .us for the US, UK for UK, IL for Israel, IT for Italy, etc. Below this top-level domain, there are other domains that they can be additionally divided to subdomain and subdomain. For example, in the case of the United Kingdom, we have a domain called AC for academic networks, and part of the AC, under the AC domain, there's say OX, which is the domain name for Oxford University. So if I look at the host www.ox.ac.uk, this means that there is a machine called www, which is belonging to domain OX, which is Oxford University, which belongs to domain AC, which is the academia domain in the UK, which belongs to the UK. The same holds for, say, NetDice, which belongs to the org top-level domain. The domain name service translates the domain name into an IP address because eventually IP needs an IP address. It cannot understand a domain name. This is only for us humans. So when I type in my browser, for example, www.ox.ac.uk, what is happening? How it is translated into an IP address? The way to do it is first, if I don't know anything about this address, what I can do, I can always go to the root domain name server and ask it, hey, where is this address? Where is this address? It might be that the domain name server does know the answer. It can send me the answer. If it doesn't, at least it can give me the IP address of the UK domain. And then I can go to the UK domain and ask this domain server, where is www.ox.ac.uk? Now, if uk.uk has the answer, it will send it to me. If not, it can give me the IP address of the ac.uk domain server. And the same with this domain server. If it has the answer, it will send it to me. If not, it will direct me to the OX domain server. This server should have the IP address of the machine called www, where the web server is located. To save all this trouble and going to all these servers, caching is heavily used in DNS. Both hosts and servers cache results of previous queries for future use. The key to having the DNS working is to have root name servers. Currently, there are certain root name servers that are distributed globally, and we can use any cast in order to approach at least one of them if we don't manage to know the IP address of a TLD that we are looking for. If you look, for example, at the K-root server, which is the one maintained by RIPE, we see that it has several locations. This one server has actually several servers located mostly in Europe, because RIPE is a European organization, but also in Korea and the US. And recently they also deployed some local nodes. These are nodes that used only in the local country or local area and are not approached globally.